Hi. Good afternoon. It's great to be here with you today. My name is Guojun Xiong. I'm a postdoc from Harvard University. My advisor is Professor Milan Tambe. The topic of this talk, the title of this talk is Aligning Task Utility and Human Preferences through LLM-Guided Reward Shaping. And look forward to sharing our approach with you. So at the heart of our research is a central theme that bringing together AI and the social science. So our primary goal is to leverage AI to improve decision-making in ways that benefit the whole society. So how do we put these ideas into practice? Within my group Team Core, we have a long-running AI for social impact program. We tackle challenges in areas like public health, conservation, public safety. And the core problem in all these domains is that how to optimize limited intervention resources. So this is where AI comes in. The need of social impact drives the AI innovation, which in turn delivers greater social impact. So we try to maximize the utility for the entire system, and these objectives often represent years of institutional learning and proven operational success with our collaborator organizations. But there's a major challenge with this standard AI approach. On one hand, we have powerful AI solvers for domains like public health, conservation, public safety, and these solvers are optimized to solve for very specific mathematical objective with years of discussion with those partnerships. But on the other side, we have human preferences who have very important but nuanced preferences that may dynamically change over time. For example, in the public health care domain, the decision makers may say that, okay, please prioritize those older patients during the flu season or slightly preference to species that are culturally significant. So as we know that these additional preferences from human was not initially designed inside of this AI solver. So there's a gap between these two parts. And traditional solver cannot automatically handle these additional preferences requirements. So this is something that we try to bridge up. So let me show you a real-world example of this challenging. We're working on maternal health in India with our partnership, Arman. This mission is to save mothers and children's lives. The scale is massive, like 20 states and over 40 million people and hundreds of thousands of trained health workers. So the problem is that they have very limited number of workers to call those beneficiaries with very large numbers. And they need to decide how to, given the limited resources, how to optimize the allocation of the course in this system. So AI can be help in this domain, but how AI can align with additional human preferences is the major challenge. Now let's look at how we translate this real-world situation into a mathematical model that AI can work with. So at the beginning, we represent every beneficiary or mothers by using a simple Markov decision process. We track whether this mother is engaged or not engaged with the health program. We call this as good and bad states. And at every week, we have a choice to make for every mother. We call her or not. So the decision we take affects the states of each mothers. For a mother who is not engaged in this program, when they receive the call, they may more easily to transit to a state that being engaged with this program. So the goal of the entire system is that given the limited budget, of course, how this AI system, to maximize the beneficiaries' engagement for the overall system. So what does the standard AI solver do? This chart can show its strategy. We can see that, okay, the conventional AI system, they heavily favor some type of mothers and some types of not. So for example, they favor the high income and high education and a very young age type of mother. Why do they do this? Because the data suggests that this type of models, they have a higher probability to be engaged in this program. And this is exactly what we tell the AI system to do, to maximize. However, in reality, right, there's a human experts may, tell us to do something opposite. Okay, this is a CEO of the Arman system. They may tell us that, okay, please prioritize those patients, in the disadvantaged type. So, given this type of human preferences, there's a gap between the original AI solver and this human preferences. So traditional solver cannot automatically handle these additional preferences, and we are trying to resolve this problem in this work. So next, let's talk about the problem formulation. So we consider a family of constraint sequential decision-making problem and define a population of n units. These units can be the mothers and animals in different domains, and each unit will be modeled as an MDP to track the states over time. And for every system, there's a limited budget or resource constraint. The AI system can only afford to provide a limited number of intervention to those units. And the goal of the original system is that task utility optimization, trying to find a policy that maximizes the long-term total expected accumulated reward given the budget constraint. And now, how do we model human preferences in this system? First, we define each individual by their features. For example, in the maternal healthcare domains, each type of mothers, they may have, ages and education level and income level and etc. Many different features. And this is a language of preferences. So the human decision makers may make some very vague or announced preferences, such as slightly preference the disadvantaged group. This leads to us to formulate a preference stratification problem, which is trying to minimize the deviation between two things. The first is the demographic mix that our original AI policy can provide, and the demographic mix of the desired or the human's preferences that they're trying to reach. So the goal is that to find a policy minimize this preference deviation here. So we have task utility for the original system, and we have additional preference certification for this system. This leads to a multi-objective problem. And our goal is to simultaneously maximize the task utility and minimize the preference deviation. And we denote this problem as G. So how do we find the best balance between these two goals? In theory, the answer is that, okay, the Pareto frontiers of these two dimensions defined as a set of points in this equation. But in reality, when we attempt to do this, it reveals two fundamental challenges. First, there's a challenge to navigating the Pareto frontier because the frontier contains multiple optimal solutions, not just single point. And how do we choose a single point requires some precise trade-off to balance these two dimensions, which in reality is a very challenging problem. And the second challenge is the imprecise human preferences because we anticipate the humans can provide a very exact numbers to control the location, but in reality, humans may just provide very vague natural languages such as slightly prefer this type of mothers. So how can we model this vague and not quantitative preferences is a big challenge. So how do we deal with this problem? As aforementioned, there are two main challenges for the original problem. So to deal with the Pareto frontier navigating challenge, we have a theoretical weapon here, the reward shaping, which can change the multi-objective problem into a single objective. And for the imprecise human preferences, we leverage large language models to shape the reward. So this leads to a new formulation of LLM-based reformulation of the original problem. And in the following slides, I will look into the details of each technique. Our first theoretical weapon is the reward shaping theory. So given a predefined weight lambda in the range of 0 to 1, to balance the task utility U and the human preference certification C, the multi-objective problem is equivalent to optimize a single objective with the shaped rewards. The key takeaway is that to solve the original problem, we only need to shape the reward function by designing an additional bonus term RH that depends on their features. And this reward and the value of this bonus term depends on the weight lambda. And lambda in reality is really hard to be defined because it comes from the imprecise human preferences and described by natural languages. So how do we deal with this challenging? We come up with a novel LLM-based reformulation of G with the main goal transfer to optimizing the prompt of LLM to generate the additional bonus reward term RH for each arms with different features. And the policy will be yielded by existing solver for the task utility maximization problem without any modifications. That means if we can design additional bonus reward term, we don't even need to do any modifications of existing AI solvers. So the procedure is that provided the optimized prompt, the LLM generates this bonus reward term, and the solvers can return the policy without any modification. Okay, to optimize the prompt, we propose the verbal guided optimization with reward tuning via experiential trajectory exploration, shorted as Vortex, quite long name. And the pipeline is showing in this figure, which is an iterative loop containing 4 key steps. So the step 1 is the LLM-powered reward generation. Given the prompt, the LLM will generate a candidate rewards. And step 2 is the policy execution and evaluation. We will collect a trajectory for this current episode K. And step 3 is the verbal reinforcement via trajectories comparison. We compare the utility and the preference deviations of trajectories in 2 consecutive trajectories, K and K plus 1. And the step 4 is the text gradient prompt optimization, which updates the prompt based on the verbal feedback in step 3. So here's a simple example of how to conduct verbal reinforcement. So LLM reflects from the comparison between 2 consecutive trajectories in the 2 dimensions and provides some verbal feedback. And then this feedback will be fed into the prompt for the next iteration of reward generation process. And we finally show that our vertex framework can converge to a Pareto optimal points under MAD assumptions. First, the external solver returns the optimal policy. The preference divergence term is convex with respect to the feature distribution, and the verbal reinforcement provides directional information with vanishing bias. So it provides performance guarantee of the proposed Vortex algorithm. Finally, let's see some experimental results of this Vortex algorithm. We evaluate Vortex on the RMAN for maternal health care domain, which contains 8 types of mothers with a total 800 units in the system, and each type of mother contains 100. And the budget is set to be 400. There are 6 different preferences we used for the experiments, like favor the high-income mother, low-income mother, favor the high-education mother, low-education mother, and also the old and young mothers. So we first show the effectiveness of the reward shaping technique. The figure on the left shows the achieved preference certification for the base reward and the 6 type of preferences we impose on the Vortex framework. As we can see that Vortex can achieve preference certification with only a minimum and acceptable sacrifice in the overall utility compared with the base reward. Base reward here means that you do not have any preferences here. So it gives you the maximum utility you can achieve for the entire system. Once you impose an additional human preferences, you will sacrifice a little bit for the utility. And the right figure shows the coverage ratio comparison for the base reward and the 6 different type of preferences. As we can there's an example here. We can see that for the base reward, we can observe that the low-income type of mothers was significantly underserved for this base reward. But if we can impose, okay, please favor the low-income type of mothers on the vortex system, it will significantly changes the coverage ratio of this low-income mother. And we can see that this coverage for low-income mothers has increased substantially in these figures. Next, we compare the vortex with the state-of-the-art benchmark DLM, which designs the entire reward function to meet humans' preferences only. It ignores the original system's utility. So we can clearly see from these two figures. These two figures comes from the example of favored low-income type of mothers. The left figure compares the total utility, and the right figure compares the coverage ratios. We can see from these two figures that vortex actually has a slightly less sacrification of the utility, and it is more stable when it is more stable and balanced better on the human preferences. Last, we present the Pareto front navigation of our proposed vertex algorithm. We can observe that both trajectories start from the single point. This is the base reward provided. Okay, start from the base single point. We can observe that both trajectories, sacrifice utility to gain preference satisfaction, and they explore different regions in the 2 dimensions. The vortex can converge to a stable, well-balanced solutions at different points, so catering to the varying stakeholders' priorities. And the takeaway here is that which Pareto point, to select it finally depends on the human decision makers' preferences. So let's wrap it up here. We introduced the multi-objective formulation to balance task utility maximization and the human preference deviation minimization. And we have an example of RMAN for the maternal health care domain. We propose a LLM-based formulation here and propose a vortex algorithm to balance these 2 dimensions. And numerical evaluation on public maternal health domain was presented, and we have more experimental results in the paper. If you are interested, you can refer to the paper. Yeah, thank you.
Time for one quick question. Any questions for our speaker?
Thank you for the great talk. One question about the results. When you were showing that the algorithm was actually adapting well to different preferences, where you showed the average number of pools, you would see that when changing for, let's say, high age or low age of participants, you get more number of pools that would satisfy the preference. But when you were going the other way around, you could see, again, more number of pools, but like significantly much more. How would you explain this difference, this asymmetry, that you still satisfy the constraint, but once you satisfy even more, and the other with not that much of a difference? I don't know, does this make sense?
Actually, I'm very sorry. I barely can hear your voice. Can you speak
sorry. Yeah. Can you go back to the slide when you're showing results about
this one?
One before?
This one?
Here, yeah. On the right. When you say that you favor low, let's say, whatever. Low, or favor old or old and young. You see, when you favor young, between like the green bars, there's a much larger gap when you favor young compared to when you favor old. Do you have an intuition on why this is happening?
Okay. So actually, I do not control the absolute value of of how with different type of preferences. I do not control the exact value. This depends on actually the inherent transitions of different type of mothers. Actually, you cannot control a single attribute of the mothers. So mothers, they have many different features that jointly decide their transition probabilities. So, you cannot analyze the single features. Here, I just present some intuitive idea here that we can somehow control that, but the exact number or level of coverage, I cannot control that. Okay, that's the point. Yeah, for a mother, they may be young age, but high income, low education, right? They may have different combinations of those features. They are jointly decide the transition probability of their states. Yeah.
Thank you, Guojun. Next up, we have Woody Zhu, who is an assistant professor of data analytics here at Carnegie Mellon's Heinz College of Information Systems and Public Policy.
Thanks. Hi, everyone. Good afternoon. My name is Woody Zhu. I'm currently assistant professor here at CMU from Heinz College. Very excited to be here. So this is a joint work with my collaborator from Harvard Business School, Michael Lee. And to begin with, I just wanted to give you some high-level ideas. So I'm kind of the researcher that works at the intersection between operations research, machine learning, and the statistics. And we have a broad interest in a wide variety of applications, including public health, transportation, emergency assistance. But nowadays, I tend to focus more on the similar challenges in the power system. And particularly, we're more interested in the decision-making problems in a high-stake setting. So one of the examples is, if any one of you are from California, you must remember what has happened earlier this year. There's a wide range of wildfire in 2018, some of these wildfires are actually caused by the utility. Whenever there's like strong wind, the tree branches touch the power line, it will cause the fire, and then the fire develop into wildfire. And it literally makes the PG&E, which is the largest utility in California, go bankruptcy. So what they wanted to understand is how they can strategically make some actions to mitigate the impact of the wildfire risk in response to those kind of extreme weather conditions. And one of the strategies is de-energize the power lines. So how do you do it? How do you de-energize the power line in a way that can minimize the risk while still make sure everybody get the power, right? So this is just give you some taste about what kind of problem that we're working at. So now I wanted to use another application as a motivating example. I have used this example many times. Probably some of you have know this example very well. So this is a collaborative project between, even when I was a PhD student, between Georgia Tech and the Atlanta Police Department way back in 2018. And that idea is we wanted to help those police officers to redesign the districting in the city, okay? Because the city is developing very, really fast, and the crime pattern is also evolving over time. So they wanted to adjust those districting plans in order to meet the demand. And more specifically, the objective is because this is the city of Atlanta, and you can see it consists of 6 different zones, and every single zone operate independently. So one of the objectives is they wanted to make sure that the police workload can be balanced across different zones. And the things that we can do is to tell them how to adjust those assignment of each one of these small geographic units, which is indicated by this gray, little area. So there are, if I remember correctly, 86 what they call the beat, the smaller geographic units, and they wanted to divide it into 6 different zones. Then how do we do it? To ensure that the workload differences across the zone can be minimized. So this is like a typical predict and optimize problem, if you're familiar with the literature, where we need to forecast how much crime activity is going to have in the next 5-10 years, and then based on this forecast, we have to solve an optimization problem. So we have a paper about it. It has published like a while ago, and the idea is we first build a predictive model, like a simulation model, that is able to anticipate the crime pattern, and then we solve a mixed integer programming. And we basically just follow exactly what the police officers told us to do to set up the problem mathematically. And we solved the optimization, and this is what we proposed for the first time. And we spent so much time just telling those people, this is the best option you should take. This is the design that you should adopt. And this is my advisor by the time, and she was literally presenting the design to Major John Quigley, who is in charge of this project. And John is, super nice guy. He said, wow, this is great. This is exactly what we wanted to have. And at the rounds of discussion with other colleagues within the department, I said, well, unfortunately, Woody, I don't think this is going to work. And there are two major reasons. So one of these reasons is they're quite uncertain about the accuracy of the prediction, right? Because nobody can guarantee what's going to happen after that 5 or 10 years. And secondly, some people may suggest, well, even though I'm pretty sure this is going to be the optimal plan, but I don't think this plan is feasible because some of the design can cut off the access to the highway, and this community cannot be separated. So there are many other physical constraints. They don't, explicitly tell us at the beginning. So there's no way we can know those kind of information. So eventually, the way how we address this issue is, well, Woody, can you just rerun the model for multiple times, making sure that all of the designs look different from each other. So we can pick the one that we like. And this is exactly what we have done. So we rerun the model using heuristic optimization softwares like semi-linearing, so that we are able to make sure that all the plans look slightly different from each other. And we presented 10 designs to the police chief, and they picked one that they liked the most. And it was implemented. It got approved in 2019, and it officially implemented later in that year. So what we can learn from this example? I've always thinking about this problem for a very, very long time. And I firmly believe there's some kind of principle behind the scene that we haven't had a chance to uncover. So the key challenge is there's a huge uncertainty in the human desirability, or to put it in another word, in the objective function, right? The original objective function proposed by the police, even though it was proposed by themselves, does not give us the full picture, right? So this uncertainty may stem from two things. So the first is the data insufficiency, right? We don't have enough data to give us the full picture. And secondly, we may have some misinformation. We may lack of certain covariates. We don't know certain constraints, or some of those knowledge can even hardly be formulated in a mathematical term. Okay. And if you circle back to the things that most of the consulting firms have done, usually these kind of high-stake decisions are made by a two-stage process. So first, usually the operational and analytical team is going to work together with the practitioner and offer a portfolio of multiple recommendations, right? And then the human decision maker is going to select the most desired option based on the preferences. If it doesn't work, you have to go back and redo the design again, and so on and so forth, until it reaches a point that everyone is happy. So I think this paradigm makes a lot of sense. So first of all, it addressed incomplete information through the conversation between the designer and the decision maker. And secondly, because of the human are still holds the final agency. So naturally, humans are held accountable, so it meets the legal and ethical accountability constraints. And last but not least, sometimes we just love to have the human to be the decision maker. When you see a doctor, right, you wanted to see the real doctor. So the talk, in this research, we try to answer this question, can we solve this problem in the principal manner? So this is the basic pipeline for the decision, like a normal decision-making problem. And usually we start with the problem objective, and we wanted to give a model about it, so it can be regarded as a predicted and optimized problem. If the problem is risk-averse, then you can use other techniques such as robust optimization to find the most robust decisions that is insensitive to the risk. Here, one of the solutions, which is actually motivated by the example that I introduced, is we wanted to introduce human arbitration into the loop of decision making. And more specifically, we have two lines of the works that trying to tackle that complement to each other but answer the same question. So the first is what we call recommend and select. Right? We wanted to recommend a bunch of solutions, and we give the human opportunity to make their selection. And the complementary framework is called the decide and validate, because usually we found humans love to make their own decision. And what we can do is to use the data to tell human, hey, how risky the decision is going to be. So these are two things, like two different line of works. Today we're going to mainly focus on the first one. But if you're interested, my student Wenbing is also among the audience. He also presenting our, the decide and validate line of the work here in the poster session. So if you're interested, feel free to stop by his poster. So let's circle back to the police example. So one of the key challenges that we haven't fully addressed is the quantitative objective didn't tell us the full picture. Right? So let's assume the L is the human desirability. It's something we want to optimize for. And it consists of multiple things. Some of them are observable. Some of them are unobservable. And if you just take expectation over the things that we don't have observation, then we can isolate the things that we have observation and the things we don't have observation. And if just reorganize this mathematical equation, you will find something that looks very similar, just y plus u. So it's sort of like a model that has a noise term, right? So the y represents everything we know, like the typical objective function. And u is something that we don't have observation at all. We have no idea what they wanted to have, but they exist. And if you simply regard u, or which is the uncertain term, the uncertain component, this is the way how we solve optimization problem, right? We just optimize what we have known, and we find the optimal solution. This is the typical way how we address decision-making problems. And now let's see what kind of issue we might have with traditional methods. So this is the L, which is the red line, indicate the true objective that we wanted to optimize for. The orange line represents something that we have observed, or something we artificially defined. And the blue line is something that we don't have the observation, but they exist there. So eventually we try to optimize this red curve. Unfortunately, we don't have observation, so we have to take a step back and optimize for the orange line. So this is set up. And if we just try to find optimal decision based on the orange line, you will find the green line, vertical line, will indicate the optimal decision. But if you look at the value of the red curve, of the green line, it is actually suboptimal, right? So now let's re-examine the idea that I proposed earlier. What about we select multiple decisions? What's going to happen? So the kind of idea is we're trying to set up this kind of two-level-like optimization problem to enable the collaboration between human and algorithm, where you have the inner optimization problem is solved by the human. Because like I said, we recommended M decisions, and the human picked one they like, right? So the inner optimization problem is solved by the human. They pick the one out of M that they like the most, which maximizes the L, right? And outer optimization is something we wanted to solve. So the pi represents the solver, or represent any kind of stochastic generated policy. It can be generated model, it can be anything, it can be any kind of stochastic policy. So we wanted to find a policy that is able to recommend M decisions so that the likelihood of the people picking the one they like will be maximized, right? I hope that is clear. So we have a generative model that is able to recommend M decisions, and humans going to pick one they like, and we wanted to maximize the chance to find their favorite decision. Here comes one of the key assumptions we have. This is the first assumption. We have to assume that a human can always make the best selection. Okay, this is something we have to bear with. Well, as everybody knows, humans always have a hard time articulate how good a decision is, right? If you ask, hey, can you give me a score to quantify how good the decision is, it's almost impossible. But if you give two decisions to the human policymaker, then most likely they will be able to find which one is better based on their domain knowledge. And the selection itself reflects the way how human express their domain knowledge is. All right? So now let's just express L more explicitly by decomposing the L into Y and the U. And here comes our second assumptions, because U is a very general, unobserved zero-mean stochastic process. In order to operationalize this idea, unfortunately, we have to give it a structure so that we will have a better idea what does the property we may have for this optimization problem. So here, for simplicity, we assume it is a Gaussian process, which is quite common in the literature. And the Gaussian process, so the U can be modeled by a stationary Gaussian process with a mean 0 and the covariance function k, which is quite important. I will talk about it later. So let's look at the main proposition we're going to have. So here, we can, with all of these assumptions, we can derive both upper bound and lower bound for this original objective function. And the one thing that's quite interesting is if m equals to, so both bounds contain the same term, and which is determined by the m. If m equals to 1, both terms go to 0. And it makes a lot of sense. If we don't give the option to human, then there's no point of adding additional information. We just optimize the y, which is the quantitative objective. And the sigma is something what we call the variance that determines how certain or how uncertain you about the objective. And the second term is the correlation that quantifies how diverse your policy is, which is super interesting. And the third thing is the sample impact, which is monotonically increasing over the m. If you have a larger m, if you give more option to the human, then you can less care about the y because you have more opportunities, right? So here, because due to the time limit, I won't be able to go over all the details, but here this is a toy example. So the toy example is saying by constructing a very simple policy, what we call the epsilon optimal uniform policy, so that we can perfectly control the diversity of the policy and the optimality of the policy. As you can imagine, if the policy is wide, meaning it's more diverse, right? You're more likely to draw the samples that look different from each other. If it is narrow, it's more concentrated around the quantitative optimal. And if you look at the result, you can find a real interesting concave curve where you can see if the epsilon strikes somewhere in the middle, you will minimize the regret and also reduce uncertainty. So basically what we're trying to solve is to strike the balance between the optimality and diversity, okay? And one nice thing about the Gaussian process, because the Gaussian process is so nice, so that we can derive as a posterior. And assuming human prefers A1 over A2, then this posterior is actually analytically explicit, right? I don't want to bore you with all the mathematical detail, but just wanted to show the example. So if we don't have any feedback at all, it's going to be like a straight line with a very wide uncertainty band. If you just offer two options, it will take advantage of the information and just cover a little bit and also narrow the uncertainty. And as providing more information, you're going to be able to, reveal the true objective function more clearly. And to operationalize this idea, we propose two methods. One is for the continuous randomization. Basically, you can just train a genetic model that can produce solutions that is desirable to human. And secondly, is designed for, it's kind of iterative approach that is designed for the discrete optimization problem. And lastly, we have a lot of numerical results. We have shown our method compared to other baselines can attain the best performance in terms of regret. And also we apply this model to the redistricting problem. And as you can see, when the sigma, which controls how uncertain you are about objective, when sigma is small, then you kind of heavily rely on the y. So you don't see any differences at all across all the training samples. But as your uncertainty grows, you're going to see that the decisions look dramatically different from each other. Okay, and we also did the same comparative experiments using this data against other baseline, and we can prove that our model attained better performance. So to summarize, for the traditional approach, they simply just ignore the U and simply focus on the quantitative objective function by finding the single quantitative optimal solutions. Whereas in our framework, we're trying to find a policy that is able to produce multiple curated solutions to enable the interaction between human and algorithm or human and the data. And also the human selection can provide useful information to help us refine the understanding of the problem itself. And that concludes my talk. Thank you for your attention. Appreciate it.
Are there any questions for the speaker?
Hey, really interesting talk. I appreciate you adding in this hue to make the problem more realistic. I'm curious if you've thought about when either the environment is non-stationary or the human preferences are non-stationary, and how that kind of
That's
interacts
a
with
great
this.
question, and there's no way we can do it, at least for now. I mean, we have to, at least for the type of the problem that we have been working on, I mean, the human knowledge certainly can override most of the decisions made by the algorithm. So we tend to believe that human is always correct. And one of the fun facts I can share with you is we have been working with a utility, and we have developed a really nice method and algorithms to deliver the decisions and present it to the utility companies until, our president candidate got shot. And we get the phone call early in the morning and say, hey, Woody, we have to redo the design. And I ask, why? I mean, everything has been approved by you guys, but why we have to redo it? And one of the reasons is because they're kind of pessimistic about the future of the renewable energy, and that will dramatically affect the design and all the details of the forecasting model. And it turns out they're correct. Because of the BBB, the bill coming out, the company is under massive layoffs and the design, and we have to change the design dramatically. So I think that the example really highlights that sometimes the humans are correct about the decision they wanted to make. And this is something that the data or the algorithm will never be able to capture. So of course, for some application, we will not be able to always assume human is correct, and the human sometimes can be biased. And that's exactly what we're trying to resolve by extracting useful human information without introducing too much bias. But thank you for the question.
Let's thank our speaker one more time.